Death and destruction sweep across the Indian Ocean.
What is happening is worse than science fiction.
It's like a gigantic train wreck. The front end stops and the back of the wave piles in and destroys everything on the shore.
It's the most devastating natural disaster of the past 100 years. A wave that kills more than 250,000 people. The world now knows the meaning of the word tsunami. But are we prepared for the next one?
There are a lot of big cities in harm's way. Who knows who's going to lose the gamble?
Nothing can withstand the awesome force of a large tsunami. But understanding how tsunamis are created, the way they speed across oceans, and how they inflict such devastation will help us cope with the next one. In the wake of the greatest tsunami in recent history, Naked Science asks, how can we protect ourselves from these killer waves? We examine how earthquakes, underwater landslides, volcanoes, and even asteroid strikes may all trigger tsunamis. Scientists pinpoint American cities where massive waves could strike at any time. We assess how effective our warning systems might be when the waters rise up for real, and how those safeguards were no use at all as a tsunami swept toward unsuspecting coastlines around Sumatra, Indonesia, on the day after Christmas, 2004.
Oh my God!
7:58 a.m. Sunrise over the Indian Ocean. The second most powerful quake in recorded history triggers a series of deadly tsunami waves. But in those first vital few minutes, only a handful of people have any idea what is about to happen. "6,000 miles away in Hawaii, barely a minute after the earthquake, Barry Hirschhorn has just come off 3 days duty at the Pacific Tsunami Warning Center. Computers spring to life as they pick up telltale seismic signals. This is a record of the actual seismic shock, which doomed more than 250,000 people, reduced to an innocent-looking line on a chart. Earthquakes exceeding magnitude 6 instantly trigger automatic pager messages to scientists. Hirschhorn tells how he received his warning at 8:01 a.m.
I'm at home with my 3 cats who I've just fed. Earthquake alarm goes off. I look at the alarm and I see that these are 2 stations in the Southwest Pacific. I realize that because those 2 stations are kind of far from each other, this is not a tiny earthquake, but I don't know how big it is. I get on my bicycle, I ride my bike into here very quickly. I'm here within about 1 minute to 90 seconds. When I walk in the door, Stuart is already at the screen here next to me, looking at the traces come in.
Dr. Stuart Weinstein is working alongside Hirschhorn when every alarm in the Pacific Tsunami Warning Center goes off.
I see the seismic waves arriving on seismometers that we have in Western Australia. And these arrivals also look pretty big. Not too long after that, we start getting automatic locations.
We locate the earthquake, we run an immediate estimate of its size, a magnitude estimate, and the magnitude estimate shows 8.0, which is huge for us, very large, and we're immediately sort of taken aback, I guess.
Hirschhorn calculates that a tsunami may already be racing across the ocean. They have a network of gauges and deep ocean pressure sensors to track a tsunami, but it only works in the Pacific Ocean. In the Indian Ocean, there are no sensors providing information.
We know we should do something. There's no regulation, no rules, no one to call. We go out immediately with an observatory message, and then we go out with our routine product immediately, which is a tsunami information bulletin.
The bulletin informs Pacific coastlines of the earthquake, but the shores of the Indian Ocean receive no such warnings.
In the Pacific Basin, we look at water level data. We have 100 water level stations plus here, as well as over 100 seismic stations. Indian Ocean, 0.
Hirshhorn is left powerless to help.
We're frustrated. We have no way to get the information out. And we also don't really know what's going on, because not only can we not get the information out, but we have no data coming in. We don't have enough data coming in to say what's going on. So we were flying blind.
Even as the scientists struggle to understand what is happening, thousands are dying on the other side of the world. People closest to the earthquake are hit by the first unstoppable waves. The waves are big, very big, and they seem to roll on forever. But it's not just their size that makes them so deadly. What makes them special is the way they are created and the way they move through the ocean. There is a fundamental difference between the mechanics of tsunamis and normal waves. Normal waves can be massively powerful, as Jose Barrero from the University of Southern California's Tsunami Research Group, an enthusiastic surfer, knows only too well.
Being tossed around by a really powerful wave is something that's difficult to get used to. It scares you every time.
Normal waves are created by wind pushing and piling up the top layers of the ocean into a swell. As that swell runs toward shore, its front end slows down as it encounters increasing friction with the ever shallower seabed. The rest of the wave, still rushing in behind, piles up against the slower moving water in a higher and higher hump. It's been likened to pushing a rug against a wall. The front of the rug stops when it hits the wall, and the rest of the material piles up in waves behind it. The height that the wave or the rug reaches depends on how much water or cloth is pushing in behind. And at sea, the amount of water on the move is determined by the length of the wave, the distance between the crest of one wave and the crest of the next.
These wind-generated big surfing breakers are still not anywhere near as powerful as the tsunami that hit in Sumatra.
Large normal swells have a wavelength of around 300 to 600 feet between their crests. By contrast, tsunami crests can be as much as 100 miles apart. That means 100 miles of water in motion, relentlessly pushing in behind the ever-slowing front end. The water piles up and up and up. The huge amount of energy contained within the water, far more than in any conventional wave, drives it ever onwards and upwards onto the land.
Instead of seeing a wave break on top of the surface of the water, imagine the entire ocean rises.
Many places are at risk of those entire oceans rising, bringing the threat of disastrous flooding. These floods in New Orleans were not a tsunami, but Hurricane Katrina did show what floods from any cause can do to a modern city. So can science protect us? Can we learn how to predict the next great tsunami? Predicting the next tsunami and preventing another tragic loss of life partly depends on understanding how tsunamis are created. Walter Dudley, a professor of oceanography, studies how movement of the seabed can generate tsunamis.
It can be faulting, which produces a large earthquake, or a big chunk of seafloor is pushed up or drops down or even moves sideways. As long as it pushes a lot of water, it can generate tsunami waves.
A vertical movement of the Earth's crust on the seafloor jolts a column of water upwards and pumps vast energy into the ocean. Which is what happened in the Indian Ocean quake. The giant earthquake shook people awake, as far apart as Thailand and the Maldives. It lasted for 8 minutes. It shook so violently that many people were unable to stand. The Indonesian tsunami was so severe because a section of almost 800 miles along the seabed suddenly flexed upwards. This vertical jolt, miles from land, forced the sea upwards by about 10 feet, producing the tsunami that reared up to become a 90-foot wall of water as it reached the coast. The force of the earthquake was roughly equivalent to a 100 gigaton bomb. That's 6 million times the power of the atom bomb that fell on Hiroshima at the end of World War II. These satellite pictures show Banda Aceh, the home of 225,000 people in northern Sumatra, before and after the tsunami. Kostas Sinolakis from the University of Southern California studied the Indonesian tsunami's terrifying destructive power.
This mountain of water that results from the motion of the seabed, the motion up, starts moving towards Sumatra. And when it hits the coast, it's a mountain of water 15 feet high and tens of miles long, moving inland and destroying like a bulldozer everything in its path.
The sheer volume of water on the move makes a tsunami dangerous. But two other factors make it even more deadly. The first is its speed.
Tsunami waves in the deep ocean travel at incredible speeds, the speed of a jet airliner. But even when they come ashore, it would probably be going more than 30 miles an hour. That's much faster than anyone can run.
Tsunamis travel so fast and so far because their energy is transmitted rapidly and efficiently through the water.
What we're really talking about is the speed of propagation of the energy pulse, because the actual water particles don't move. It's the energy pulse as it goes through the water medium that moves.
The principle can be demonstrated with a Newton's cradle, a popular executive desktop toy. The energy of the first swinging ball travels from globe to globe with hardly any movement at all of the central balls as the energy pulse passes through them. It's similar to the way tsunami energy moves. The water particles move a little bit forward, and then they move backward and end up right where they started. There's a second factor that makes a tsunami so lethal. It remains a silent and almost invisible threat till the very last moment. While at sea, the waves may be only a few feet high. They can even pass under a ship unnoticed. Only in shallow water does the height climb dramatically as the pulse or shock wave converts into a wall of water. The length of the tsunami pulses as they come ashore can be more than 100 miles long. They flow onto the shore like a relentless river, sometimes for over an hour, unlike a conventional wave, which breaks, then withdraws after a few seconds.
The way to understand how tsunamis can be relatively benign in the deep ocean but so destructive on shore is because of the wave length. That is the key component to their destructive nature.
The front end of the wave is slowing and hitting the shoreline, while the rest of the wave, which may be 100 miles offshore, is still rushing in and piling up on the back.
It's like a gigantic train wreck. The front end of the train hits the wall first, and then the back end of the train continues piling in and destroying everything in its path.
The impact can be truly devastating. Unstoppable walls of water that drive on and on and on. Dr. Simon Boxall from the Southampton Oceanography Centre in Britain explains why a tsunami overwhelms all in its path.
Each yard of water, each cubic yard of water coming towards you, has the weight of 1 ton.
It's the equivalent of a car hitting you at 40 to 50 miles per hour.
And if you put it in that term, then you start to understand the force that occurs when that wave hits the beach. It's totally destructive.
And tsunami waves rarely travel alone. A series of waves can crash in, sometimes hours apart.
There can be multiple pulses in a tsunami wave train for a variety of reasons.
Ladies, get out of the street! It's coming again!
One is that the source was able to produce 2 or 3 waves, and there may be 2 or 3 waves propagating from the source area. It's like when you throw a large stone into a pond. Even though there was just one impact of the stone, you still get many waves rippling across the surface of the water.
The creation and effect of a tsunami can be replicated in miniature in a lake, in a rock quarry. Dumping 300 tons of sand displaces water and pumps energy into the lake. An energy pulse travels from water particle to water particle. As that energy travels through the water, it shows as a barely visible bulge on the surface. The tsunami becomes more pronounced as the water gets shallower toward the edge of the lake. The energy from the shock wave continues to push the wall of water from behind, producing the characteristic relentless, seemingly unstoppable flood ashore. Contrary to popular belief, tsunamis do not have to be huge waves. These ripples across the pond are every bit as much a tsunami as the one that devastated the Asian coastlines. But here, the energy input to the water was infinitely smaller, with infinitely smaller tsunami results. This mini tsunami demonstration shows the deadly dynamics in action. Even though the artificial trigger here was utterly different from the natural phenomenon that caused the Asian disaster. In fact, there are many ways to generate a tsunami. They can be triggered by undersea landslides, or volcanoes, or even by the massive impact blast of an asteroid from space. How can we predict future tsunamis? The Indian Ocean earthquake and tsunami dominated headlines around the world for months after December 2004. But that was not the first time a major natural disaster in Indonesia had hit the front pages. More than a century earlier, a tsunami struck the region, but that one was not caused by an earthquake. In 1883, the volcano Krakatoa erupted. It was probably the loudest sound ever heard by humans. Reported to have been heard 3,000 miles away, it's the equivalent of an explosion set off in New York being audible in San Francisco. The blast created 130-foot waves, which crashed onto the nearby coasts and killed 36,000 people. A volcano such as Krakatoa can cause a tsunami in more than one way.
Now, obviously, if a volcano erupts, you get the explosion effect, and that creates a shockwave, which is a tsunami in the water.
But then there are volcanic pyroclastic flows, scalding clouds of dust and ash speeding down slopes. At the ocean, they can displace enough water to create a tsunami. In July 1998, thousands died in a tsunami caused by an entirely different natural phenomenon. Near Papua New Guinea, north of Australia, an earthquake measuring 7.6 on the Richter scale jolted the seabed. Within minutes, 50-foot-high waves crashed against the low-lying north coast. There was no time to flee inland, and the tsunami killed more than 2,000 people. Scientists found that this tsunami was caused not by the earthquake itself, but by a landslide under the sea.
What we saw in Papua New Guinea is that what we call a moderate earthquake shakes the seafloor. It triggers this landslide, which is like a submarine avalanche. And the avalanche itself creates this huge wave.
Underwater landslides happen when a shock to the seafloor sends sediment, rocks, and mud rolling down underwater slopes toward the ocean floor. The slide displaces vast amounts of water, forming a tsunami. Sinolakis insists that the Papua New Guinea tsunami provides surprising new evidence that underwater landslides are a far greater hazard than scientists had previously thought.
For the first time, we saw what a giant landslide can do. It can trigger a massive wave that is highly localized, and wherever it strikes on the coastline, it completely inundates everything in its path.
This underwater landslide theory has made scientists reassess tsunami risks all over the world. It suggests that a huge tsunami could result from a severe or moderate earthquake if it happens in just the wrong place. Near coastal areas, there may be unstable underwater slopes poised to fall and trigger a tsunami. Scientists classify them as surprise tsunamis because they can strike without the warning signs normally expected from large earthquakes. But for really surprising tsunamis, scientists look to the skies rather than under the ocean. Earth lives under the slight but constant threat of an asteroid strike from space. And as recently as 2004, a 100-foot-long asteroid passed within 27,000 miles of the Earth. The chances of a large asteroid hitting the Earth are slim, although many experts believe that a 6-mile-wide asteroid led to the extinction of the dinosaurs when it plunged into Mexico's Yucatan Peninsula 65 million years ago. The impact catapulted debris into the atmosphere and blocked out the warmth of the sun. Temperatures plummeted, and over years, plant life died, and the dinosaurs could not survive. If it had landed in water instead, the destruction would have been felt around the world within hours.
By looking at the sediments of the sea floor, we can actually see various stages in our history, in the planet's history, where there are particles of meteorite dust or particles of asteroid.
And an asteroid crashing into the ocean is still a terrifying disaster scenario for humankind. Using our quarry demonstration, we can see how a large object smashing into the sea causes a wave. If an asteroid 3 miles across slammed into the mid-Atlantic, waves would inundate large parts of Europe and much of the eastern United States, racing far inland to the foothills of the Appalachian Mountains. Chances are Earth will take a hit from an object that large once or twice every 10 million years or so. But even smaller asteroid strikes can cause cataclysmic events. And they are 2,000 or 3,000 times more likely, perhaps hitting us once every few thousand years.
If that hit the ocean reasonably fast, then it would create a wall of water, initial wall of water, the splash, if you like, would certainly rise maybe 1,000 feet up into the air. You'd find a tsunami of significant size. We're talking here 50, 100-foot size. So we can only guess as to the size of the devastation and the destruction that would take place.
Millions could die in such a disaster. And like most tsunamis, the destruction would come in a series of waves until the water finally settled back to its original state. Whatever their immediate cause, one thing is certain. Tsunamis of every type have been a threat for as long as humankind has existed. There is little that can be done against the awesome power of such waves, other than running away and sheltering on higher ground. But we need warnings to know when to run. To predict future tsunamis, scientists are studying this coastline, where parts of an island were jolted 5 feet into the air by an overwhelming natural disaster. Scientists are looking for ways to tell when future tsunamis may strike. So far, we've seen how rare events such as exploding volcanoes and asteroids can generate deadly tsunamis. But the most common threat remains that from powerful earthquakes, like the gigantic movements at the edges of the tectonic continental plates. In the wake of the Indian Ocean tsunami, some scientists fear the possibility that another earthquake along the same fault line could trigger yet another deadly series of waves. Scientists are seeking ways to predict when such waves might occur. For that, they need to predict when earthquakes might happen. One of the first tasks is to uncover the history of earthquakes around these coasts. Charting that history is Kerry See, professor of geology at the California Institute of Technology, who's been studying earthquakes in Sumatra for the past 10 years. Just a few days after the 2004 tsunami disaster, he makes an astonishing discovery on the Sumatran island of Simeulue. See finds that the whole island has been tilted by the force of the earthquake, causing land submerged beneath the ocean for thousands of years to be thrust out of the water. See and his team can easily measure these recent changes by using a series of GPS measuring devices that can track the movement of the land. These work by locking onto satellites and are accurate to hundredths of an inch. The urgency of See's work was demonstrated just 3 months after the 2004 tsunami disaster. On March 28, 2005, there was another earthquake, triggering another local tsunami.
This instrument showed that the land moved up 5.5 feet during the Nias-Simeulue earthquake in March, and then it moved out about 8 feet to the southwest toward the ocean.
These latest land movements were comparable with the sort of land shifts that occurred here during the main Asian tsunami. Parts of Simeulue moved around 5 feet up in just a few seconds during the December 26th earthquake.
There's a big earthquake fault beneath this town, about 15 miles. So these people are the first ones to have felt the earthquake as it began.
The 2 recent earthquakes and tsunamis are dramatic proof of how unstable the Earth's crust is in this area. But how does an earthquake fault line cause such a sudden, dramatic uplifting of land? The answer lies deep under the ocean. in the geological makeup of this region. It's an area where vast tectonic continental plates collide. These plates are constantly in motion, giant rafts of rock driven by convection currents deep within the Earth. But this is not a smooth slipping of one surface over another.
One way to think of the join between the two is to think of a ruler. If you hold it in one hand, you can pull it down, and then when you let go, it springs back up again. Well, the land is very much like that.
All Sea's modern equipment gives exact readings of recent land shifts. But they offer no clues at all to the island's seismological history. So Sea and his team are turning to an unlikely scientific tool: the island's coral reef. Sea believes that coral, lifted from the water in earthquakes, can help him establish the elusive historical pattern of earthquakes in centuries gone by. Coral thrives underwater as a living reef, but it dies once it's raised up into the air. The dividing line between live and dead coral is therefore the perfect indicator of how much the water level has changed. Caltech geology graduate Richard Briggs is one of Sea's team. It's his responsibility to create a map of the huge uplifts around the coast of Simeulue.
145, got it. Well, we're trying to figure out how much the land moved here, how far it came up or how far it went down. The coral here has come up out of the water at least a meter. When that happened, the corals that were living here just died. They're up and out and in the air.
If you know how to read the signs, the coral holds even more detailed clues as to what has happened on this island over hundreds of years. Each time the land uplifts and the coral dies, a new ledge of living coral carries on growing outwards just below the surface of the water. It forms a series of ledges on the coral heads, each ledge revealing the level of low tides during the year of its creation. To better study the history of the coral, Sea and his team have obtained a permit from the Indonesian government, giving them permission to dissect one of the newly exposed coral heads. The only way of doing that is with a chainsaw. The process is like cutting through a tree trunk and counting the rings to discover how old it is. But it takes more than just one coral head to paint the full picture.
We have to take heads like this modern one, and we have to take other heads like the ones sitting back near the beach that are older, and we put together a whole story over hundreds of years. We put together a story of how often the giant earthquakes happen. Right now, nobody in the world knows the answer to that question.
By learning the history of uplift on these islands, Sea will know how often massive earthquakes have occurred in the past, a historical timeline that may help him predict them and their associated tsunamis in the future. Those living around the Indian Ocean need help right now. Work is continuing on a tsunami early warning system here. But will it be ready in time to prevent further tragedy? Some parts of Asia will take many years to fully recover from the effects of the 2004 tsunami disaster. But even as the rebuilding continues, there is evidence that another giant earthquake could strike the Indian Ocean soon. Scientists and governments are installing an early warning system for the region to save lives in a future tsunami. But will that system be in place in time? And how effective will it be? The model for an Indian Ocean early warning system already protects the Pacific. Seismometers staked out all around the Pacific can almost instantly pinpoint the size, location, and depth of an earthquake. And other instruments detect if a tsunami has been triggered.
We have seafloor gauges now which can actually measure tsunami waves at sea. So we'll know how much energy is being propelled in a particular direction.
The Deep Ocean Assessment and Reporting of Tsunamis Project, DART for short, anchors pressure recorders on the seabed. These sense the overlaying pressure of water and can detect the extra volume of water carried over their heads by a passing tsunami. The sensitive instruments can detect a tsunami just half an inch high. Waves from ships and storms are discounted because such near-surface waves are not deep enough to reach the sensors. If a tsunami is confirmed, the warning is passed on to national governments around the Pacific, and local evacuation plans are put into force. Dr. Charles McCreary is director of the Pacific Tsunami Warning Center in Hawaii and is actively involved with developing the new warning system for the Indian Ocean.
The technology is there to measure the tsunamis propagating in the deep ocean, and this information can be used to make accurate forecasts of tsunami waves for places that haven't yet been hit.
Once an earthquake happens, if we have direct tsunami detection in the open sea, we can forecast how big the tsunami will be when it strikes the coastline.
Few doubt that a DART system in the Indian Ocean will save lives, but not all the experts are convinced an expensive high-tech solution is the complete answer, especially when there's a danger of an earthquake close to shore.
There were loud cries for early warning systems so that couldn't happen again. People would have a warning. But I think now that we've had time to ponder what happened, we can sit back and we can say, look, let's figure out first where they're likely to happen next.
It turns out that there are areas much closer to home than the Indian Ocean that could be at risk from tsunamis. And since the earthquake faults in such areas lie close to shore, the DART warning system may be of little use or even no use at all.
There's more than 100 cities of over 500,000 people that are within 100 kilometers of a major active fault. Who knows who's going to lose the gamble?
One risk area could be the west coast of the United States. A devastating tsunami could be triggered by earthquakes on fault lines off the coast of California. Just offshore, the Monterey Bay underwater canyon has 2-mile-high, steeply sloping sides. Even below the surface, the instability of these slopes can cause underwater landslides, with resulting tsunamis heading straight for the shore.
This will create a wave that will flood Monterey, Moss Landing, part of Santa Cruz, all the low-level areas around the bay.
A tsunami would easily engulf the Santa Cruz boardwalk, submerging souvenir shops, arcades, and unwary tourists alike. Much of downtown Santa Cruz would be underwater in seconds. But it's not just the West Coast that's under threat. One controversial theory is that the eastern seaboard and parts of Europe face possible disaster. On the tiny island of La Palma, off the northwest coast of Africa, some scientists fear that a 120 cubic mile section of the Cumbre Vieja volcano could collapse into the sea at any time.
If we have had the flank collapse, we will get a wave that will reach all the way to Florida.
Such a collapse could generate waves 1,000 feet high that would devastate the area and roll on toward mainland Europe. Although the theory has been criticized by many geologists, it suggested waves traveling west across the Atlantic could still be 7 stories high when they crash into the cities of the east coast of the United States. It's been 560,000 years since the last time the Cumbre Vieja volcano caused an undersea landslide. But some scientists believe another event on this scale is bound to happen sooner or later. A third area under threat in the U.S. is the northwest shore of the states of Washington and Oregon. It's the location of the Cascadia Subduction Zone, or CSZ, a 680-mile-long fault line that runs up the Pacific coast from Northern California to Vancouver Island in Canada. Here, the Juan de Fuca Plate dives under the North American Plate, and every 200 to 600 years, it does so with an enormous jolt. Although subduction earthquakes along the CSZ are rare, when they do happen, they can be massive, magnitude 8 or 9 on the Richter scale. The Indian Ocean earthquake was 9.1. The earthquake that destroyed San Francisco in 1906 was 7.9. So just how prepared is the Pacific Northwest? Because the risk is so real, the Northwest coast is already a designated tsunami hazard zone. Being prepared for a tsunami means planning for two very different scenarios. In the first, an earthquake somewhere out in the northern Pacific generates a tsunami. The waves could take hours to reach the Northwest. Ample time for official warnings, whether by sirens or other methods. In theory, people should have plenty of time to round up their families, pack their cars, and follow marked evacuation routes to higher ground. The second scenario is far more deadly. Imagine a major earthquake striking just offshore. Lynn Smith is communications manager at the Tsunami Warning Center, as well as being part of the team for the local 911 service for Seaside, Oregon.
The ground would shake so significantly in this building that you would have difficulty standing.
A tsunami would race toward the shoreline, leaving precious little time for the residents of Seaside to evacuate.
This community has to evacuate immediately. We have a window of 20 to 30 minutes before the series of waves start to arrive.
The ground would barely have stopped shaking by the time the first wave hits. Ken Murphy is the Director of Emergency Management for the state of Oregon and has spent almost 30 years managing disaster areas for the U.S. Army.
Many of these people are not residents of this area and may not know what to do. They may be injured or killed because of the tsunami or just by debris that the ocean may bring in. Most people would have a tendency, they're going to start running, hopefully in towards their cars or their hotels.
You cannot evacuate everybody. We're limited as far as our evacuation routes because of the rivers. Lives will be lost, it's guaranteed. Will there be a panic? I would imagine, yes, there would be a panic.
Oh my God!
The advice for people in this case is simple and straightforward. As soon as the ground stops shaking, drop everything and run to high ground. Try to reach 100 feet above sea level. Don't wait a second before fleeing. Half an ocean away from Oregon is Hilo, Hawaii. The town learned to react to a tsunami the hard way when it suffered great losses in 1946. It was inundated by a tsunami generated by an ocean floor earthquake thousands of miles away. Curious locals came to see the wave for themselves. They had no inkling of the damage it was about to wreak on their town, and 96 people lost their lives as a result. Walter Dudley believes that education of the public and the authorities is the surest way to save lives.
They need to understand what to do when there is a tsunami warning. And for those people who are closest to the point of generation, there may well not be time for a warning. So they need to understand nature's warnings of a tsunami. They need to understand the phenomenon. And we have good examples from the tragic Indian Ocean tsunami of a few individuals who understood what was happening and managed to save not only their lives, but the lives of many people around them.
Perhaps then, the most effective way to remind and educate is a back-to-basics public awareness campaign. For many people, information posters on the causes and dangers of tsunamis may prove to be more effective in saving lives than the much more complex and expensive solutions being proposed for the Indian Ocean.
So Nias and Simulu, laut juga harus laut. Okay.
The remote Indonesian island of Simelu is the closest inhabited land to the center of the enormous 2004 quake. On mainland Sumatra, 110 miles further away from the center of the earthquake, thousands died. You might think that the death toll in Simelu would also run into thousands. But something different happened here. Across the Indian Ocean, people thought the danger was over when the shuddering stopped. But the Simeluan islanders knew the worst was yet to come. They remembered the warnings of their grandparents.
This whole island knows that 100 years ago, in 1907, there was a giant earthquake, and it produced waves taller than the ones that were produced this time. And thousands of people died.
The islanders grew up with stories of that terrible event and remembered the warnings passed down through the generations by the survivors. On December 26, 2004, waves as high as 33 feet smashed into the villages along the coast here, sweeping away homes and buildings. The community was devastated, but of the island's 75,000 inhabitants, only 7 lost their lives.
The place is so close to the source. To have a complicated electronic system that would actually warn people, you don't need it. You know, these people felt the earthquake for 3 minutes. As soon as it allowed them to stand and to walk, they ran to the hills, and not a single person lost their lives in this town.
The lessons learned over 100 years before are preserved in these close-knit communities where family ties remain strong. This time, when the earthquake struck, they knew what to do.
When the water went out, we knew what would happen next. We knew it would come back deep, and it did. The whole village was underwater, but there was no one left there, so no one died.
On this island, past experiences saved many lives. But sometimes there is just no way of planning for or preventing disaster. In December 2004, the human race was given the ultimate reminder that nature can deal a deadly blow. A functioning early warning system for the Indian Ocean and a better public information program could have saved thousands of lives in countries such as Thailand and Sri Lanka. But those closer to the epicenter of the giant earthquake could not have been saved by even the most sophisticated early warning system. The deadly power of undersea landslides, earthquakes, volcanoes, and asteroids can all cause tsunamis. If we are to prevent another tragedy like that of December 2004, we need to understand better the science of tsunamis. As yet, scientists still cannot accurately predict when and where the next tsunami will strike. The truth is that right now, they can offer no more than an educated guess.
There are a lot of big cities in harm's way and don't know it and are not capable of doing enough about it.
The most effective thing we can do is to have public education so that people know when to evacuate to high ground.
There's a great deal of interest right now and awareness of tsunamis because of the tragic Indian Ocean tsunami. But humans have notoriously short memories, and I fear that in a few years a lot of this awareness will be lost. You don't have to live in fear of tsunami waves, you just need to be prepared and know what to do.